Dear participants, I do hope you're all safe and healthy, and I would like to extend a warm welcome to you all at this very important quantum event we are organizing in collaboration with Quantum Amsterdam. My name is Gijs Boudewijn. I'm General Manager at the Dutch Payments Association. For us, at the Dutch Payments Association, the quantum adventure began in 2015. That year, the Dutch Secret Service told us about something mystical, the quantum computer and its possible impact in the context of cybersecurity. At the time, we of course had no idea what these guys were talking about. So what do? We organized information sessions with crypto experts of our members, and we asked the Secret Service to elaborate on what they believed the impact might be. Quite soon, it became clear that the relevant impact of quantum computing for us would focus on the encryption technologies we are using in payments. As early as 2016, Daniel J. Bernstein, Tanja Lange, and Peter Schwabe gave us an insight into the cryptography research of post-quantum cryptography. And in 2017, we invited academia to help us understand developments in the quantum-related hardware and software, and when a powerful quantum computer might become available. The industry was confronted with a lot of unknowns and uncertainties, and we had no clear view or compass how to navigate the uncharted quantum waters ahead. So how do you plot your course then? We have used their findings as input for sessions with our banking experts, and we defined multiple low-regret moves, such as, of course, a no-brainer, follow the developments in quantum computing and post-quantum crypto. Second, maintain and expand the current inventory of payment processes that use that encryption. And thirdly, encourage international financial organizations to also prepare for the arrival of the quantum computer. The first point in particular prompted us to organize brainstorming sessions with experts to determine whether and how we should adjust our cybersecurity policies. Keeping track of the developments and creating awareness across the industry is obviously a good and a no-regret thing to do, and there is a lot of interest, as evidenced today by the fact that for today's event we have over 2,000 international registrations. Quantum is indeed a global phenomenon, maybe the new blockchain. Ladies and gentlemen, the quantum computer, as any technological development, is not just a threat. It also offers great and exciting opportunities. The best part of it, as has been explained to me as a layman, is that it takes less effort for us to use quantum computing to protect the payments industry and our customers' wealth than the effort it would take criminals to develop a real threat to the encryption technologies we know today and help protect that wealth. It sounds reassuring, but somehow I have an uneasy feeling about such assumptions. But anyway, I finished. I encourage you to explore and actively gain knowledge and experience in the possibilities that quantum computing offers, and I wish you a very stimulating and fun event. Thank you.
Thank you, Gijs, for opening the session for us today. And good afternoon again, everybody. My name is Maran van Heesch. I work for TNO as a cybersecurity expert and work on the quantum domain already for 5 years. Welcome, everybody, to this digital studio. We do this in a digital way. We all know why, but it doesn't mean that we should not be in touch with each other. Today there will be 2 ways to get in touch with me or our speakers of today, and that is via the YouTube chat or via Squiffer. And you can see the logo of Squiffer in your view. You can go either to vincent.squiffer.com and log in, or use the QR code in the screen. And you can use both platforms to ask questions to our speakers. And I see the first people coming in, so welcome. Today we have a lineup of various speakers from both industry and academia, experts all in their fields. And I hope this session will help you find your path in the quantum world today. A little bit further, taking steps together. Our first speaker is Harry Buhrman. He is the executive director of Qusoft and also a group leader at CWI and a professor at the University of Amsterdam. So I would like to welcome Harry Buhrman to the stage. Welcome, Harry.
Hello, Maran. Good to see
Good
you.
to see you. Good to see you.
Yes.
And I look forward to your talk on the musings of the future quantum software, giving us the first glimpse into what a quantum computer might be able to do.
Yes, and might not be able to do. I'll just quickly go ahead because I don't have too much time. Thank you for the introduction, and thanks for organizing this. It looks all very interesting and exciting. And I want to say a little bit about quantum software, an area that I started working in the late 90s already. And then in 2015, I realized that a lot of the focus on quantum computing was made on the quantum hardware. And you have to realize that not only the hardware is fundamentally different, also the software is, because it uses quantum mechanical effects like superposition, interference, and entanglement. It's also quite challenging to find out when a quantum computer is useful and when it's not. And so to put more effort into that, in 2015, I launched together with CWI and the University of Amsterdam the first research center, I guess, worldwide on dedicated solely to quantum software called Qusoft. And in 2017, we got additional funding from the government to form together with Leiden and Delft the Quantum Software Consortium that is focusing on very similar aspects that Qusoft is. So a few words about what we do at Qusoft. We have grown currently to about 25 permanent faculty. As I said before, it's joined between CWI and the University of Amsterdam. We have about 50 postdocs and PhDs, and it straddles the fields of computer science, physics, and mathematics, and is actually currently also venturing into chemistry. We have a couple of themes that you can see here in this little diamond, where we focus on algorithms that can be run on near-term or current technology, the so-called few qubit applications. And we have algorithms that work on future quantum computers that have more stable qubits. Then there is a theme called cryptography in a quantum world, where we look at how the world looks like from a secure point of view when quantum computers are there. And then there is a theme called quantum information science that is sort of blue sky research. And a few years ago, also industrial partners started to show a lot of interest. And we have research projects with Bosch, for example, and ABN, and others are on the way. And so we have also now a business and society side to Qusoft. And moreover, we engage with the national agenda and industry. And actually, that led us to have a new theme along these four called Quantum for Society and Business. And all of this somehow connects well with the newly formed hub Quantum Amsterdam that is organizing this very workshop that you are present at. So an important problem that needs to be addressed is which computational problems have a quantum speedup? And I actually get this question a lot. And unfortunately, there is no crisp and clear answer. Actually, it's a very deep and fundamental question, and I don't think there is an easy criterion that tells you which problems have a speed up and which ones don't. But roughly, you can categorize the world into three categories, namely those problems that have an exponential speed up, like factoring and quantum chemistry simulations. And for example, this factoring is important because that breaks a lot of currently used cryptography. Then there are those problems that have a polynomial speed up, like backtracking, search, and satisfiability solvers. And then thirdly, there actually is a very large group of problems that does not have any speed up at all. Those are really, really hard problems, like counting, for example, the number of satisfiable assignments for formulas, but also very easy problems like edit distance, sorting, and binary search. And for example, doing word processing, that's probably not going to have speed ups on your quantum computer. And one warning here is that all these categories, they could vanish if certain hypotheses that we don't know how to prove turn out to be false. And those hypotheses are P is not equal to NP or stronger ones like the strong exponential time hypothesis. And I won't dwell into that, but bear in mind that all of this is somehow lives on unproven hypothesis. And for most problems, we actually don't know in which category they fall. So here we have these computational problems that some fall in no advantage, some polynomial, some exponential, and a bunch, actually most, for which we don't know yet how things are. And this is the traditional classical way of looking at things, and there are 3 problems with that, and I want to address them quickly and then discuss how to solve them. The first problem is actually that the quantum hardware that we currently have and that we will have in the foreseen future is actually far from perfect. It is noisy and it will deteriorate quickly over time. This is called the NISQ devices. And we have these, and in order to use them, we really need new quantum algorithms. So the ones that I've talked about before, we don't really know how they run on, how to run them on NISQ devices. So we need new quantum algorithms that run on these noisy machines. Moreover, a second problem is that traditionally we look at the worst case advantage that algorithms have. And we're really interested in practical applications in what the true advantage is. And so we need something that's called quantum heuristics. And then third, all of the analysis is asymptotic. And there's a nice complexity theory behind this. But we really need to argue about actual instances that have a particular size. And also that is something that needs to be addressed. And I won't address that now, but I will quickly talk about number 1 and number 2. And when we have addressed all these, I will call that quantum software 2.0. So the problem of noisy qubits is that these qubits deteriorate over time, which means that you can only use them for a very short amount of time. So that means that you have to run your quantum computer for very short times and then alternate that with classical computation in between. And moreover, since the readout is probabilistic, you have to repeat this whole process many, many times. And this is somehow the regime that you have to deal with. This means that you have to run your quantum computer often and for short periods of time. And this computation mode is called also hybrid computation, but a lot needs to be said about that and needs to be explored still. There are a couple of frameworks that we currently have, but they are not sufficient. The one is the QAOA framework, and the other one is the VQE framework. We work within them, but we don't really know how well they work. A somewhat broader framework is that of shallow circuits, where you look at fast, short, quantum parallel time computations. And one interesting point here is that Shor's algorithm that does factoring, that does the factorization problem, and that actually is a threat for security, that can actually be run on these shallow circuits. So actually Shor's algorithm is not that far away with respect to this hardware. And a fourth point is that we will have Hamiltonian programming, where we want to make optimal use of the quantum hardware that's available. So that goes below sort of assembly language, quantum assembly language that we currently use. But note, it's not clear how well these techniques really work on the NISQ setting, and new ideas and fine-tuning both for hardware and software is needed. And the second problem is that of worst case versus real case, and I think it's best to see that by means of a little example, where if you have traditionally, you see the orange graph here, that is the classical algorithm and running times, and the yellow one is the best quantum one. And you see here that on instance 2, the two algorithms have the same running time, and traditionally you would say, well, there is no quantum advantage here. But that's of course not true, because you see here on these other instances, 2, 3, and 5, you see an advantage. And now if you were allowed to design an algorithm that isn't faster on all algorithms, but that is maybe slow on instance 2 and 1, which maybe never occur in practice, but is really fast on instance 4 and 5, then you have a quantum heuristic algorithm that is really, really fast. So quantum heuristics is something that we need, but that we cannot really try out because we don't have a quantum computer to run on it. So we need the theory to reason about these, and some examples are set solvers and pattern matching. So quantum software 2.0 is that where we have to design algorithms that run on these NIST devices, and also algorithms that run in a heuristic setting, and probably a combination of these two. Now, feeding into the end of my talk, I see a couple of feedback loops, namely those that deal with the hardware, where academics running together with mathematicians and talk to experimentalists. And then on the other hand, you see a same cycle within industry. And these hybrid algorithms, they really predominantly figure on the hardware cycle, whereas this quantum heuristic approach works on the industry cycle. So summarizing my talk, we have quantum advantage 1.0 that has these three problems that I just discussed, and then quantum software 2.0 partially addresses these three problems. And on top of that, I see these feedback cycles that do co-design on one end with quantum hardware people, and that do some research together with industry to come up with real case instances and quantum heuristics. Then, Maran, I want to end with a warning, and the warning is that the field, to my opinion, is way too overhyped with a lot of unrealistic claims. And these claims are, for example, it will very soon, and it is here, quantum computing and quantum technologies will very soon change the way we do computing, and it's a disruptive technology that's pervasive to everything. And these claims are way too strong and way over the top. Moreover, lots of money is being poured into this by venture capitalists and other programs. And I think this is overheating the field. And the truth, of course, is that we are still at the very beginning of the field. It's in its very early stages, perhaps comparable to the 40s or 50s of the classical computing area. And we will not have useful quantum computers in the next 5 to 10 years. That's just the truth. We won't have them. And the field is at the moment still in a very much exploring and academic mode, and we should realize that. So quantum computing is nevertheless extremely interesting, and it does have potential, but I urge everyone to be realistic. Thank you.
Well, thank you, Harry, for this presentation. I think you gave us a lot to think about, especially also with the warnings you just posted on our screens. I have one question from the audience, and that is, what business models are there for companies to use quantum computing, in your opinion?
Well, at the moment, I still think these business models are a little bit too far away. So in the next 5 to 10 years, I think the business model that we can have and that industry can look at is to have somehow a joint project together with perhaps academia or perhaps some small companies that guide these industries through the emerging field of quantum computing and quantum technologies. But still keeping in mind that it's going to be a joint journey with no quantum computer in the next 5 to 10 years available.
All right, thank you very much, Harry, for your insights on that. Then I would like to invite our next speaker to our digital studio today. That is Leo Ducas. And Leo Ducas, he is a cryptographer and also a crypt analyst at CWI. He works there as a tenured researcher. And he is specialized in lattice-based cryptography, and actually is working on several post-quantum cryptographic schemes, which are currently a finalist in the NIST standardization process. So Leo, welcome to the studio, and I look forward to hear your presentation.
Thank you very much, Maran, and thank you to the organizer for this invitation. So I am here today to speak about quantum-resistant cryptography. So this is cryptography that is meant to protect yourself against the threat of quantum computer, but that runs on classical hardware, so that you don't have to change all your infrastructure. It's pretty much just a software update that we have to prepare for, because cryptography migration takes time and effort. And today I will discuss a little bit the standardization process that is going on quantum resistant cryptography, and also issue several recommendations. Let me start by discussing what modern cryptography looks like. So cryptography is not only about encryption. Cryptography is about more general security property, confidentiality, so that's encryption, but also integrity and authentication. And this is digital signatures. And they are crucial to the current way we protect networks and communication. And the modern way to do cryptography is to do cryptography that is provably secure under some assumption, computational assumption, such as the following one, the assumption that factoring large integer is intractable. Why do we do this? Well, it allows us to not have to study the crypto system as a whole, which is a very complicated object with several parties interacting through time, but instead focus on this very simple mathematical problem. I mean, it's not simple in mathematical sense, but it is simple to state. We can focus on this. And cryptanalysis is the exercise of testing those assumptions. This is one of my specialty. So your aim as a cryptanalyst is to invalidate an assumption and therefore to discard the schemes that goes with it, but also to quantify what infeasible or intractable means, so that we can select key size when we actually make standards out of those cryptographic designs. Again, I want to emphasize that modern cryptography is not just encryption. We have something called public key cryptography that gives you a very paradoxical thing. Until the 70s, cryptography always required parties who wanted to communicate to have pre-distributed keys. So they would have to physically meet in a room and exchange a key, and no one else should ever learn what happened in this room. So this makes application of cryptography very limited. It was mostly used for diplomacy and military purposes. Public key cryptography, invented in the 70s, has changed all this and has made cryptography much more useful, especially for commercial application, in particular happening today over the internet each time you open a page. Nowadays, two parties can communicate securely even without any prior interaction. And this is a very important point, because when you connect for the first time to a website, you've never met with the designer of the website before, okay? How is this done? This is done with three cryptographic primitives, namely digital signatures. They will offer you integrity and authenticity so that you are sure that the person you're talking to via your computer is indeed the person you want to talk to. There is no man in the middle. Then there is public key exchange, which allows you via a channel that is public but now authenticated to create a shared secret. And therefore, you can use this shared secret in symmetric encryption for exchanging long message or video or audio or whatever data you would like. So far, so good. This is public key cryptography. So how do we construct public key cryptography? Well, we are basing ourselves on those mathematical problems such as factoring or elliptic curves. And the issue that we are having today is that those techniques, those mathematical platforms, they are threatened by quantum computing. There is this algorithm called Shor algorithm that would break them if we had a quantum computer. This was theoretical for a while, but recently, given the current progress in quantum computing and the increasing investment, some concern were expressed by serious agencies such as the NSA. So the NIST has decided to react by calling for the standardization of quantum-resistant cryptographic schemes. So here I want to mention that it's not like we have to invent it from scratch. Research on post-quantum or quantum-resistant cryptography has been going on for decades. The only remaining task is to push its technological readiness. Okay, so it's a matter of implementing, testing, standardizing, and finally migrating. I also want to clarify a distinction between quantum-resistant cryptography and what is called quantum cryptography, which you might have heard also quite a lot in the news. So let's start with the cryptography we have today. It's for a world where no one has access to any quantum device. Both the user and the attackers just have regular computers to play with. Quantum-resistant cryptography is for a world where a few quantum computers would exist. So that is the threat that we're talking at the moment. Maybe something that's going to happen in 10, 15 years. And in this world, we must assume that it's the adversary that has the quantum computer, because the NSA or the Chinese mafia or whatever adversaries, they probably have more means than you to try to break cryptographies, and you have to use cryptography. So it's a David versus Goliath kind of situation. And both quantum-resistant cryptography is meant for this scenario. Finally, quantum cryptography is for a world where quantum devices are ubiquitous, and not just devices, also the networks. It means that you have to dig trenches and put a new network of fiber, of special purpose fiber optic to unlock this quantum cryptography. So this is definitely not for the next decade. We're talking maybe 40, 50 years in the future. I also want to clarify that quantum cryptography is not going to solve really the problem that you're currently having. Quantum-resistant cryptography, on the contrary, will give you exactly the same features as the cryptography you're using today. So basically, you will have symmetric encryption, public key exchange, digital signatures, but also all those very cool advanced cryptographies that you can use for secret auctions or elections or cryptocurrencies like zero-knowledge proofs. And all this at the cost of new interactability assumption, but you will still have the same logic, the same processes. So you'll have all your favorite crypto at just the cost of a software upgrade. You might lose a little bit on the performances, but you just need to switch to new mathematical platforms, but all the rest of your infrastructure will be unchanged. Quantum cryptography, on the contrary, doesn't have all those primitives to offer. We essentially have quantum key distribution and quantum randomness. So you'll have to upgrade your hardware or even your network infrastructure. You will have very limited functionality. You don't have all this advanced crypto. It is very at a very low technological readiness level, and it is also very hard to audit. Sometimes it is claimed that there is nevertheless a very good advantage, which is that it does not require interactability assumptions. So we have more confidence that it is secure. This might be true for a very small set of applications, which corresponds to application of the cryptography before the 70s. If you want to establish secrecy between two parties without prior interaction, then you will still rely, for example, on signatures. So you will still need quantum-resistant cryptography, and in particular, you will use interactability assumption. So I think at the moment, given the current state of technologies, there is no debate about whether you should go the quantum-resistant road or the quantum crypto road. In particular, agencies such as the NCSC have made very clear position paper about it. They do not endorse quantum key distribution for government and military application and advise for quantum-resistant cryptography. Okay, so where is quantum-resistant cryptography at? So we have 20 years of research, and we are now at the standardization phase. There has been 3 rounds at the NIST standardization process. We started with 73 candidates. We are now down to 7 finalist candidates and 8 backup candidates. What are the next steps? Well, maybe within 1 year, the NIST will have selected a portfolio of standard. Not just one standard, they will give you some room for choice because different application might have different performance constraints. And maybe 1 year after that, we will finally have standards published. In that period, there will be a draft that will be improved. So I also want to mention that each of those candidates, at least each of the candidates that passed to round 2, have been backed by very serious teams of international experts. For example, the candidates I'm involved in at CBI were the joint effort of 6 partners, including 4 universities and 2 industrial partners. So among the solution for quantum-resistant cryptography, we have some choice. There are 6 different platforms: Codes, Lattice, Multivariate, and some others. And a few of them will appear in the portfolio. That is what to be expected. And as I mentioned, some are very mature. They have 20 or even 40 years of research behind them. So there is no serious reason to be very worried about the transition. I want to conclude with a few recommendations. The first one is do not panic. It's not like you need quantum-resistant cryptography implemented and ready tomorrow, but you might need it within a few years. So you should start preparing now. How can you start preparing now? You can read TNO's Guide on Migration, which is very accessible but very precise. You can join our next symposium specialized on post-quantum cryptography, joint symposium by CBI and TNO. And the last reminder is that it's about security. It is not about innovation. Don't get blinded by the shiny. There are people that are going to try to sell you what we call snake oil cryptography. There are always people trying to sell snake oil cryptography, but the transition to quantum resistant is going to make this even worse. So don't be blind by the shiny. Follow the standard, get certification, go to serious vendors if you need to buy external advice on post-quantum cryptography. Thank you very much.
Thank you very much, Leo, for your presentation. And I like your ending with please don't panic. But also, just as Harry, you have some warnings for us. So it's good to get your insights in this. We have one question from the audience, and that is, what is a safe bet to have post-quantum encryption implemented for financial institutions?
So I'm not exactly sure what the question is about. Like, is the question about which of the 6 mathematical platforms you should choose?
I don't have a direct line of contact with the person who asked the question, but I think that's a very interesting question. If you could answer that one.
So, I mean, I work on lattices, so they are kind of my favorite, but my best argument for choosing lattices is that they give you both encryption and signatures, whereas each of the other solution only give you one, so you would have to use 2 different mathematical platforms. Also, lattices will give you even more than just signature and encryption. As for getting everything implemented, you probably won't have to implement things yourself. The NIST standardization process comes with reference implementations. There will be many vendors offering you specialized implementation if you're using smart cards or non-standard computer hardware. Probably the talk from NXP will go over this.
All right, that gives us some insight in the program ahead. But first, thank you very much, Leo, for your presentation. And I think we might have some Q&A or some questions for you in the Q&A later today. I already see that Stavros Kousidis has joined us in the digital studio. And Stavros, you are a cryptographer from the Federal Office of Information Security in Germany, and you actually led the study you've done on the development status of quantum computers. So I look forward to hearing your presentation, and I wonder if your views on the current state of quantum computing and post-quantum crypto is also the same as we just heard from our academic partners. So Stavros, the floor is yours.
Thank you, Maran, for the introduction, and thanks to the organizers for the invitation. So I would like to tell you something about the status quo of quantum computing, at least from the perspective of the BSI, the Federal Agency for Information Security in Germany. So I guess every talk about quantum computing today starts with telling you that if there's something that we call a universal quantum computer pops up tomorrow, then this renders basically any public key cryptography that we use today useless. So I just listed some of the cryptography that we use today in the internet.
It's RSA, it's DFM and Ergamal, it's DSA, and ECC stands for elliptic curve cryptography. So what that means is that nothing of the following remains. It's we don't have any key exchange anymore. We don't have digital signatures anymore. We don't have public key encryption anymore. And just to keep it simple, it means that we fall back to a time where no public key cryptography existed. This is what Leo Ducas was telling us before the 70s, before RSA and Diffie-Hellman was invented. We had only pre-distributed keys. So confidential and authentic and integer communication will be very, very, very difficult. So just to be a bit more precise, why is that? I would like to tell you, how do we measure how secure a cryptographic mechanism that we use today is? We measure this and we coin a term that we call a security level. So before telling you what the security level, or before putting a security level into perspective in front of quantum computers, let me take a step backwards and talk about the computers that we use today. Our smartphones, desktops, servers, which are digital computers. So what we do is we measure the security of a cryptographic mechanism in terms of how many operations does it take to break cryptography. So, and what we have is this number 2 to the 100. It's really a huge number. I will put this into perspective in a minute. So 2 to the 100 is BSI's entry level for security for classified information. The entry level is what we call VSNFD. It's restricted, so restricted information. So just to tell you why 2 to the 100 is really a huge number, 2 to the 50 operations in some amount of time, let's say, is what we can do with our supercomputers today. And to put this into perspective even more is the age of the universe in seconds is in this order of magnitude. So you could say a supercomputer today could simulate every second of the universe, something like that. So just to talk about concrete algorithms that you might have come across it's AES-128. You all use it. If you don't know it, you use it, definitely. In your messenger, in email communication, in any encrypted kind of communication, confidential communication. So the security level is basically 2 to the 128, more or less, okay? And just to give you another cryptographic algorithm that you really use, some of you every day, it's RSA 2048. Maybe you don't use 2048, but you use RSA maybe. This is really at the entry level, at the entry security level of BSI. So for example, RSA, if you have an OpenPGP certificate for email communication, you might have an RSA key. So let me put this into perspective when we talk about quantum computers. So now we do not measure operations on a digital computer, which are binary operations. Now we have quantum operations, whatever that is. It doesn't matter for now. But let me tell you, RSA 2048, to break this will take 2 to the 30 operations on a quantum computer with an algorithm that we already have heard of. It's Shor's algorithm. And maybe to put the second algorithm that I've given you in perspective, it's AES-128. It will take roughly 2 to the 64 quantum operations to break this. And this is something that the NIST, the National Institute of Standards and Technology in the US, that does this post-quantum standardization process, has defined as security level 1. So it goes up to security level 5, which corresponds to the security of AES 256 when you consider quantum computers. So maybe this is a great amount of numbers. So let me just say, you know what 2 to the 30 is. it's gigahertz. Every one of you knows what 2 to the 30 is, because this is the amount of operations a gigahertz processor can do in a second. So the picture when quantum computers enter the world to execute Shor's algorithm to break RSA changes drastically from the digital computers that we have today. Okay. Okay. So really, to get to the point, the central question is: do we really expect a quantum computer that, including something very crucial, overhead coming from quantum error correction, can solve a gigahertz problem? This is really the central question. And to try to approach an answer, not to give an answer, but to approach this, the BSI funded a study. It's available under this link. It's in English. You can download it. And what we really did is to spot technologies, qubit technologies for building quantum computers, and to put them on some kind of in some kind of perspective, how advanced they are. So from entry point A, they meet some basic functions. Going over to B, they have some kind of quality in their operations. From C, they allow implementing state-of-the-art error correction. Going over to D and E, which says that, oh, I can implement a full-fledged quantum algorithm like Shor on them. And what we found is that this is not very surprising, maybe, but is that 2D transmodes, that's basically Google technology, and ion traps, which is, for example, IBM technology. They are the most advanced platforms. And what we did for them, what we did for them is we did an extrapolation. We took 2D transmodes and we really disassembled what kind of overhead comes into the picture when we talk about quantum error correction. And what we found is that the quantum elementary operations, to break RSA 2048, would be that you have to do 10 to the 15, which is, let me compute this for you, 2 to the 30 times 10 to the 6. So gigahertz times roughly the number of seconds a year has. So even with the overhead coming from quantum error correction, quantum computers pose a theoretical, at the current stage, a theoretical conceptual threat to currently deployed cryptography. So I liked Harry Bowman saying, just try to keep realistic about this. But he also said that we anticipate NISQ devices, noisy intermediate scale quantum devices. And what this says is that quantum is kind of alive. So we have quantum as a service. We have big players that try to commercialize quantum. We have a service, Amazon Braket. We have Microsoft's Azure Quantum, and we have IBM Quantum, where even you as a private person can log in, create an account, and compute on their NIST devices. And the biggest NIST device at the moment is 65-qubit IBM Q Manhattan. So this is very far from really a universal quantum computer, but it started getting commercialized. So, and just let me summarize on my last slide what the BSI's positions are. So we have a working hypothesis. We say for higher security applications, our hypothesis is that cryptographically relevant quantum computers will be available at the early 2030s. Just be careful about this. I'm not saying that quantum computers will exist in the 2030s. This is our working hypothesis for high security applications, like when security level is 2 to the 200 and above. So we have updated our portfolio, which is summarized in the BSE technical guideline. If you Google this acronym there, you will find it. We have included Proto-Chem, Classic Mckinsey, and Hash signatures for high security applications. And I share some opinions about quantum key distribution mentioned by Leo Ducas. But if I say, if you want to use it, please do it only in hybrid mode with post-quantum cryptography. You will have the bandwidth anyway, so you can put in classic McAleese and you don't care about the size of public keys. And another thing that I would like to point you to is that BSI released some recommendations where we tried to give some recommendations to industry. In the moment, it's in German. We are working on an English translation. If you Google this title, you will find the document. The link is a little bit unnice. Thank you.
Thank you very much, Stavros, for your presentation, and also thank you for the clear recommendations you already have for all of us in the migration strategy for post-quantum cryptography. I have one question for you, and that is, what do you see as the biggest problem in developing a quantum computer at the moment?
It's quantum error correction. So it's really the heart of quantum computing. So you also have to be a little bit. You have to differentiate what you mean by a quantum computer. So if you are happy with NISQ devices, then they are already there. If you are thinking of quantum computers from the point of view of cryptography, then the state-of-the-art knowledge is that we will need a universal quantum computer, and really the quantum error correction is very difficult to scale up to a level where it becomes cryptographically relevant.
All right, thank you. So we have to keep our eyes open for more publications on quantum error correction. That's really a red flag for you. All right, Stavros, thank you very much for your presentation. And then I would like to introduce the next speaker, which is Joost Renes. And he is currently a cryptographer and security architect at NXP Semiconductors in Eindhoven. He's actually working on innovation projects related to post-quantum cryptography. So Joost, the floor is yours, and I'm excited to see what you're working on.
Thank you, Maran. Thank you for the introduction, and thanks to the organizers of the symposium for inviting us to share our thoughts. So I'm very happy to have had such great speakers before me who did a lot of the introduction into post-quantum crypto and quantum computing already. I think it was Leo who said that the migration to post-quantum crypto, it will take time, it will take effort, and might come at a bit of a performance loss. So basically this talk, I would like to share some of our thoughts on the migration and some of the performance losses that you might encounter in the embedded domain. So maybe to set the context of the talk, so what from NXP perspective, what we see is that there are a lot of interesting questions related to quantum computing. We've already seen some in the previous talk as well. Questions like, how long will it take for a quantum computer to be large enough to be a threat to crypto? Or what will a quantum computer even look like? Or what will the software look like? But from our perspective, we are not too interested in those questions. Instead, what we see is that post-quantum crypto is really already happening right now. Standards are being developed. There's a lot of industry interest. The Googles, the Microsofts, they're building implementations. And so basically post-quantum cryptography is already here, even though quantum computers may still be a little while away, at least large enough ones. And so what do we deal with at NXP? So we are in the embedded domain. So what do we mean by embedded devices or embedded systems? So a couple of examples. You could think of your modern car. Modern cars could have hundreds of chips in them. These chips can communicate to each other. They can communicate to external components. So maybe other cars, maybe traffic lights. You can also think of industrial applications, IoT. Nowadays, many devices have to be smart. You can have smart speakers. You can even have smart juicers now. But you can also think mobile applications. So maybe payment terminals would be an interesting one for this symposium. Mobile payments, but also transit. transit applications, and also communication infrastructure, so think Wi-Fi or 5G or ultra wideband. And so there's all these embedded systems around us which are being used. Many of them have some security components to them. And so when we migrate from classical crypto to post-quantum crypto, the question to us is, what is the impact on all these various systems? And so first question to ask is then, when we have these systems, so where do they use crypto? How is crypto or cryptography really relevant for them? And there are many use cases, and I want to highlight a couple of interesting ones. Usually we split them up into kind of two paradigms, although often these are combined. So we consider applications that use digital signatures and applications that rely on key exchange. And for digital signatures, the goal is often authenticity or integrity. In our case, often of firmware. So for example, if you have a payment terminal, you want to make sure that the software or the firmware that's running on there is the software that you intended it to be. And this can often be determined at boot. So you have protocols which ensure that the software that's booted is authenticated and the one that you intended it to. But also over-the-air updates is a good example. So when you have a car parked at home and you don't want to drive it into the garage to update it, you can maybe update it from distance. And there you have specific protocols which require digital signatures. And these two are particularly interesting in the setting of post-quantum cryptography because they can often be seen as kind of a backbone to your security. If you cannot guarantee the integrity of your firmware, it's hard to guarantee any kind of security of any software running on top of that. And so therefore, it's kind of a stepping stone to securing other parts of your system. And so when you want to migrate your system, this should be considered to be one of the first ones to be migrated to post-quantum. And kind of a happy benefit of that is that in many cases, you're a bit unsure how long it will take until quantum computers will arrive, and you're not sure whether your whole system needs to be migrated to post-quantum secure versions. Then you might consider simply only updating secure boot flow or your over-the-air update flow, so that even if not your whole workflow now depends on post-quantum cryptography, you'll at least allow yourself to update in the future. And kind of another happy benefit of these protocols is that they often don't rely on actually signing yourself, but they only rely on digital signature verification. And in practice, you see in many of the post-quantum versions of digital signatures that the verification is often much easier than the signing. Okay, and so there are other examples related to key exchange. We have an embedded system. It might have a secure element that a host needs to communicate with in a secure fashion. So this might be done with a post-quantum secured key exchange. Okay, so a little bit more concretely, so if we actually want to migrate, what will that do to our actual workflow? And let me maybe start on a positive note. And so here I drew a table with 4 schemes. So the top scheme in red is X25519. You might be familiar with it. It's a elliptic curve based key exchange protocol. And below that are 3 lattice based cryptographic protocols. So it's not too important how they work. Rather, these are 3 of the 4 finalists in the NIST post-quantum key encapsulation or key exchange standardization competition. The 4th one is classic Mckinsey, but I will exclude it because its large public key is very hard to deal with on such small devices. And the numbers that I present here are taken from the PQM4 library on a Cortex M4, so it's an ARM-based processor. And the PQM4 library is often used in the academic literature. But the main point here is that we see that the performance-wise is actually quite good. So lattices are actually very fast. They have very low latency. And so that if you migrate from your elliptic curve scheme or from RSA to a lattice-based scheme, in terms of speed or latency, you might actually not take too much of a performance hit. On the other hand, if you look at another part of the system, which is memory usage or size of your scheme or your implementation, the picture is actually quite different. And so here we have the same scheme, so top elliptic curves, and then the three same lattice-based schemes. And here we're looking at the stack usage in bytes. And so for X25519, the stack usage is below a kilobyte. Rather, for the other three lattice schemes, the stack usage is several bytes. And this does not even include yet the memory usage for public keys or for ciphertext, for example, which for lattice-based schemes are actually much larger than for classical schemes. So they also need to be stored somewhere, which puts additional constraints on these devices. And in many use cases, these devices can be really small, so they may actually only have 1 to 4 kilobytes of stack memory available. So it's actually a really serious challenge to even implement these schemes on these devices in the first place. It doesn't mean that all hope is lost. These numbers that are plotted here are very implementation specific. So often it's possible to reduce the stack and trade off some performance by doing so. But I think what it kind of shows is that inherently these schemes do need a little bit more memory. And so it will be kind of inherently a little bit more tricky to implement these. Okay, and so maybe a kind of a separate topic. So also many of these small systems, because they are very resource constrained, what they do is they add an additional coprocessor, which is specialized towards performing cryptographic operations. So for classical systems, RSA and ECC, these are often integer multipliers. So for RSA, you might need to multiply 3000-bit integers. For ECC, you might need to multiply 256-bit integers. However, for many post-quantum schemes, and in particular lattices, the operations are slightly different. So you have polynomial multiplications. And so a very interesting line of research, which kind of started by Albrecht and others, is to look at how to reuse these coprocessors that are already in systems now, to reuse them to be able to migrate quickly to post-quantum systems and not have to go through the time to develop the new hardware. Okay, so let me conclude since Maran just joined my session. So some final conclusions. So for NXP, indeed, it's not, we don't worry too much about the question when a quantum computer will be here. Rather, we worry about questions of how post-quantum crypto will impact the current infrastructure. So standards are coming, the interest is there. We see requests for post-quantum crypto increasing. And so for us, I think it's a really interesting time to be working on that. And maybe because people are putting warnings at the end of the talk, let me also put a warning here that the implementations that I talked about here are not hardened implementations. So they work, but they're not protected against adversaries that try to shoot at your device with a laser or try to measure the power consumption. If you want implementation secure against those kind of adversaries, the implementation constraints will even increase much further. So let me conclude there.
All right, thank you very much, Joost. Interesting talk, also to see what you already are working on. I think a question that came in right before you showed your last slide, but the question was, can you comment on underlying secure hardware requirements to facilitate secure boot firmware?
Yeah, so that is one of the topics that we are looking into right now. I'm not sure if the question is really specific for post-quantum or just in general.
Maybe we can scope it for now to post-quantum. Do you have any insights already?
Yeah, this is one of the things. I think it depends a little bit. So what we are hoping to do is to reuse existing hardware to also be able to support post-quantum secure boot flows. I think it's very device specific. whether this will be possible or not. And so whether new hardware is required or not, it's not completely clear yet.
So ongoing investigations needed there.
Yeah, absolutely.
Okay, so I think it came clear also from your presentation, it still takes a lot of work to implement post-quantum cryptography correctly and in an efficient way, such as we can use it. Thank you for your talk, Joost. And I hope to see you back in our Q&A session later this afternoon.
Yeah.
Thank you very much. I would like now to invite our last two speakers of today to the stage, and they will provide a duo presentation. So I would like to invite both Niko Mohr and Henning to the stage. Niko Mohr, he's a partner at Mckinsey in Düsseldorf in Germany, and he's actually leading McKinsey's global quantum community. Additional to being an assistant professor of innovation management at the University of Regensburg. And then Henning, he is also a partner from McKinsey, but then in Frankfurt, leading the McKinsey Technology Institute. So I think these are the two men within McKinsey really leading the quantum revolution there. Niko, can I give you the floor?
Yeah, thank you, Maran. Let me just kick it off and lead you into our presentation here. Thank you for the invitation, and we will build on what we have heard from the other speakers, basically. So we will focus on three main questions. So the first question we will touch is a little bit about why is quantum computing relevant, or is it relevant at all at the moment? Then we will focus a little bit on what is the adoption and maturity of quantum computing in the financial sector, and finally we will touch the space of use cases and talk a little bit about this. So let's look into the relevance question. Basically, we share the observation and the comment from Harry in the beginning that it is kind of comparable to the years of the 1940s and 1950s with Konrad Kruse and the traditional computer. But what we see is that the development cycle is much shorter, and time span is much shorter. So basically, what is happening here is that the field of quantum computing is evolving. This is confirmed by a number of companies who are now heavily investing into this, and those are very large companies like IBM, like Microsoft, like Google. Then the second point is that we see and hear the first breakthroughs. They are still kind of, let's call it baby steps, but they at least reach the point that the press is basically taking those baby steps and communicating heavily about it, which then leads to the fact that the seafloor of our clients is now more and more looking into this, which means that the economy is now trying to better understand the impact of quantum computing, or the potential impact quantum computing might have in the future. So yes, it is relevant, or it is becoming more and more relevant. And this is also underlined by the fact that investment money and funding is moving heavily into that space. Harry also mentioned this in his first presentation. Of course, it is kind of a, let's say, a bias in terms of money doesn't mean development, but it definitely means that it has increasing importance. So what we see here is, on one side, that over the last 4 to 5 years, the volume of PE investment money has more than doubled, and the number of quantum computing startups founded has also more than doubled. The interesting fact here is that less than 10% of the investments are are moving into software. So most of the money is moving into the hardware space and into hardware players. And this is for a very simple reason, that there is still some main groundwork to be done to really make quantum computing work. So as stated before, there is still some time to go until we will see quantum computing in real life. So what you can see here is just the list of the top 10 investments which have been directed to hardware players. And as you can see, it's mainly the US who is leading the pack here. There is still a question mark behind China and Asia. So data points here are very rare. In-depth knowledge of what those guys are doing is not easy to find. But what we can see is that at least for the rest of the world, the US and also Canada is leading kind of the pack here, and most of the money is moving into hardware. So with having said this, I will hand over to my colleague Henning to talk a little bit about the adoption and maturity of quantum computing in the financial sector.
Sure, and thank you, Niko, for the introduction. So just to say, what we see is, as Niko has pointed out, there is a big hype, if you want, around quantum computing. But if it comes to who is actually already advanced in the actual application of real quantum computers, who is actually advanced in also the first versions around quantum simulators or quantum cryptography, what we see is it is not like we're already at the industrial scale yet across many of the sectors that we look at. We've done a survey with about 300 companies where I try to identify where do these individual companies or where do these individual sectors currently stand. And what comes out is, of course, there is a front runner, which is not very hard to identify, around the telco and the technology space. But if we look at finance and insurance, this is rather in the range of being a beginner or being an amateur with the usage of quantum computing. So taking this into account, now you could say, okay, like possibly this is not a big topic for them, but essentially the opposite is true. And therefore, we also wanted to take a bit of a view in terms of what are actual use cases, specifically also for the financial services industry, that could be relevant going forward. So if we can just jump to that section as well, where we go a bit into the typical use cases. So the first thing is, and that is quite interesting, there has been a big shift, and I think some of further examples we will also see later in the discussion. We really see that there are examples of applications of quantum computing in financial services, and we've just collected 3 typical examples over here. But people really start to identify that there are a couple of typical use cases that are quite relevant in this space. And specifically, number one, of course, in the optimization space. If you look at insurers and banks, what they need to do in terms of risk calculations, in terms of trading, in terms of other typical real deep optimization problems. This is a perfect application of these new algorithms that have been coming out around quantum machine learning, around portfolio optimization. So here we really see that there is a lot of possible applications if these would become available also of actual quantum computers. There is a second big area, and we'll dive a bit deeper into this one as well, around cryptography. Because for insurers and banks, the actual truth is their business model is built on trust. If you don't trust, then you have the biggest problem in these respective institutions. And the possibility of breaking the respective security protocols is one that essentially goes throughout the actual business model. And this has these two aspects around cryptography and security. If I'm able to intercept communications, for example, between an ATM and a bank, I'm in possession not just of this individual source of money, but I will be in possession also of a big source of possible mistrust in the company itself. And just to illustrate why we also see that many have thus far been quite interested, sort of specifically also in the security space, is what you also see on the next page. Because when we look at the possible breaking of algorithms like RSA, in principle, of course, sort of this is something which is maybe 10, possibly even 20 years out. But we see that specifically banks and insurers live on a big estate of long-term data and long-term legacy systems which they will need to hold. So already today, you need to think ahead. How would I actually ensure that such systems would be secure going forward? And what is the data that I would actually need to secure within these systems? What is the relevant and critical data that I need to do? So it is really about already today preparing for these kinds of scenarios. It is not necessarily about the implementation of premature solutions. And before I think we can drop for sort of maybe one or two questions, just wanted to say also on the final slide, sort of we're not alone. McKinsey has done quite some work also in terms of publications within the quantum area, but specifically also if you look at what we have thus far, sort of what you need to do as a company is really to build the capabilities to also see what is the progress in the world of quantum computing, what is also specifically in terms of data tagging and data identification, what is risky. And finally, of course, also minding the hype around some of the topics. Not everything is sort of immediately applicable in industrial context. I think, Maran, we cannot hear you yet.
Yes, I'm sorry. Thank you for your presentation, Niko and Henning. It's very insightful. Also, the slide in which you show all the different organizations and in which phase of the curve they are with respect to quantum technologies. We have some questions from the audience for you. And the first one is, what are your views on potential market imbalances when the first movers commercialize quantum computers?
Yeah, let me take that one. So yeah, that's definitely a great question. So first of all, we still and the similar question came up a couple of minutes ago. There is still some time to go until quantum computing will be commercialized. So and it will definitely take huge investments until we will be there. So that means basically that, of course, those guys who then will finally have the breakthrough have a clear competitive advantage. On the other side, what we see at the moment happening is that we don't see a world of quantum computers in the near future alone. So we are currently envisioning more hybrid networks where quantum computing or quantum computers are playing a kind of hub and spoke role in the middle of a network of traditional computers. So in the end, it will end up in, let's say, a world of partnerships with those companies who will own quantum computers together with others who will add additional computing power to this.
All right, thank you. And then maybe an additional question from myself, if I may. You mentioned that there still is a lot of investment needed to actually build up to scalable quantum systems. And who do you think will pay these investments?
Maybe let myself just comment sort of on this one quickly. So what we've seen are sort of two big sources of funding, also in the past. I think sort of those would be also the ones in the future. Number one, sort of there are a lot of government programs that we see thus far, also with the quantum flagship program of the European Union that will fund for it. The other source that has become interesting is sort of all kinds of PE funds or similar aspects funding individual startups. And the interesting thing is sort of for PE funds to be relevant, this is not necessary that these startups already become profitable tomorrow. Because what essentially they are interested in is sort of, can we fund a vision? Can we fund the one possible first mover that Niko was just referring to that will be able to break it? Because there is a possible upside in terms of market value that is almost unmeasurable sort of for these first movers, which would have the technology at hand. So specifically for the PE funds, there is a big play around this, which is quite relevant for them also in terms of possible growth rates and in terms of possible multiples of such companies. So we would presume that these two sources of funding would be the major ones also in the future. There is a third source of funding from corporates who would fund their own quantum programs. However, what we see thus far is sort of they're in most cases essentially rather small scale, and we see them sort of in most cases closely tied to the respective government initiatives to also acquire funding from those sources additionally.
So 3 potential sources, of which 2 are most likely. I see in my private chat here that we have also a visitor from the embassy of Canada, and they had a very interesting comment to make. She says, thank you for mentioning Canada. So it's nice to see that we have also a very nice international audience. Thank you very much for your presentation, Niko and Henning, and I hope to see you in the Q&A session. So also for our audience, if you have any questions left for them or any of our previous speakers, start preparing your questions and let us know what you want to know. Then we have an opportunity to ask all of our speakers later. So thank you for your presentation. Thank you again. And then I would like to invite our panel to the stage. Our panel consisting of representatives of the Dutch financial institutions. We have Adil, Mischa, and Dimitri. Adil is leading the quantum journey for ING. He's actually doing research on quantum algorithms for machine learning and also focuses on the migration towards post-quantum cryptography. Mischa, he is the lead product innovation and also head of the quantum lab at Rabobank. And Dimitri, you are the quantum lead and also a solution architect for ABN AMRO in the innovation group there. So it's amazing to see that all of the 3 big banks in the Netherlands are already working on quantum and that you are now also together in this panel. So thank you very much for joining. For our audience, if you have any questions to the representatives of our Dutch financial industry, let me know. Then I have the opportunity to ask these questions to the gentlemen in our panel. A first question I would like to ask, because we have seen what quantum computing can bring, and we have seen something of a threat, but I wonder, for example, Adil, how do you see quantum technology? Do you see it as a threat or as an opportunity?
Thank you for the kind introduction and for the very nice question. So personally, I would be much more motivated by the ambitions of the second quantum revolution, where we actually bring quantum mechanics and information theory and technologies together to change the interface to the quantum world. So what we then intend to do is to actually manipulate the quantum states to our own purposes. And by doing so, this will actually make many things different that lies within the hearts of individuals, organizations, nations, and institutes. And missing out due to opportunities taken by these competing entities is a threat, likewise as abusing these technologies to combat one's security lines is a threat as well. And therefore, I think it's wise to take the opportunities and the threats seriously and place them in the context of the user, which is ourselves, our proponents, and our opponents. And that's what we are actually focusing on both the opportunities and threats.
All right, thank you, Adil and Mischa. Do you think the same of quantum technologies, both an opportunity and a threat at the moment?
I think it's both, to be honest. It depends profoundly on the way we act and when we act. When we take adequate measures on time, it will be an opportunity, but if we wait too long or don't act appropriately, it will definitely become a threat, maybe even in such a way that it will be a systemic. That said, I also want to look at our leaders to give us the opportunity and also to act timely and sufficiently.
Yeah, so timely acting is important to make sure that you are on the right side on the opportunity side of quantum technologies instead of on the threat side.
Yes.
Nice. I think that's it's a very good statement to make, and as I think Leo Ducas mentioned in his talk, don't panic yet, but start investigating to be on time. Dimitri, I have a question for you. Do you think it's possible for banks to take joint action in this?
Of course there is. Hope you can hear me. I had some audio issues, but Maran, thank you for the opportunity to be here. It's actually very, very, very nice to be here together with ING and Rabobank. Because if we go a little step back to when we started our quantum program in 2018, we said one of the things why we wanted to do it is to start now and see if we can cooperate with other organizations later. And that actually happened. So there is a need for quantum. It is big. It's bigger than just for ABN AMRO alone. And there is a need to work together on this. And we also said, if one or two companies get interested in what we're doing, then, it's one of the objectives that we wanted to get. And, I can say there's more than one or two. So we're good in that sense. And then if you talk about, what is this field that we're in and what are we talking about and what are we as a bank? The world is becoming more and more connected. And it's not just people or devices, but it's also organizations, companies. And so what are we? Are we just a single bank with our own systems, or are we part of this financial network? And if you look at the network today, we are connected. We are all connected to one another. PIN machines, watches, ATM machines, people checking their mobile apps more often in a week than they did previously checking their bank accounts in a year. So it's all about those connections. And that's why it's so important to really start focusing on what we need to do and what we can do to make sure that this system, this network, is protected now and in the future. So how are you going to do that? Well, that's a big question, and we don't have a clear answer on that. It also depends on when things are coming to a real threat, so to say. And we'd also like to follow up on what Harry Buhrman said, about his warnings. Don't panic yet. A lot of people are saying a lot of stuff, but you don't need to believe all of them. And if you look the Terra Quantum publications recently, it's a good example of how not to communicate about it. But what can we do? So what we first did with ING and Rabobank is to find common ground for us to work together. So obviously we are competitors, but also in some fields we need to work together. You can take a look at AML, or in fields of security, cybersecurity. So in those fields we can really complement one another, and sometimes we need one another. Then the next thing is, okay, how are you going to structure this? And this can be different in each country. And then also contracts, NDAs might need to be signed, etc. And once you've established that, you can then start exploring the use cases. So we explored use cases, and we found use cases, and we defined projects. And now we're taking the next step to see, okay, who are the partners that we need to do those use cases with, and how long will it take, and what are we exactly going to do? Because it's also about finding the right partners for you. And we are, I would say, lucky in the Netherlands, because we're a very, very small country, but we got a huge expertise on quantum compared to what's outside of it. So that really is beneficial because it's really hard to start communicating from an enterprise point of view to a science point of view, because they're talking different languages. So right now in COVID times, we need to do it remotely. But I can tell you that within the quantum projects that we did, we started remotely, but we got together after 1 or 2 remote meetings, because that was way better. So that's sad. If you look at the fields that are most interesting, it is for us security, cybersecurity, protecting ourselves, especially creating this future-proof financial network. And I'm happy that we're making the right steps, the right progress together. There's a lot of work happened already, also in the fields of education, because also we need to make sure that, Adil is much more a science guy than I am, so he can blow me away in 2 minutes. But we need to make sure that we're all on the same page and that we understand each other. So those kind of things in how to build such consortia or quantum projects together are important steps. And we're taking them. We're not there yet, but we're getting there. And I'm pleased to see the progress in that.
Yeah. Thank you, Dimitri, for your answer. I'm lucky enough to see some of the collaborations at close hand. And Mischa, do you also think collaboration is key in this area?
Yes, of course. We should work together in a way to create possibilities for the entire industry, because we can never do changes on our own. If a bank on its own takes measures for quantum encryption, that just doesn't work, because it always goes beyond your own boundaries, and you need to interconnect with the other banks and other parties as well, both banks, consumers, and other companies, of course.
Yeah, I agree. So in the security aspect, collaboration is key also because everything gets connected. You want to, of course, have interoperability between all the systems as well. Maybe moving forward from the quantum threat and looking more at the opportunities, I was wondering, for example, Adil, what would you like to achieve for ING using quantum computing?
So what we'd like to achieve is to actually enhance decision making, to actually have performance improvements within the financial industry. So it does not mean that we should only focus on quantitative finance, but on a much broader field within the whole banking industry. Like Dimitri said, for example, maybe later, anti-money laundering could be a very nice use case to actually make sure that the banks can perform their functionality well within actually the given tasks that they are actually assigned to. So what we do then at ING is to actually try to explore these use cases. And some of these use cases might be also non-competitive use cases that can actually enhance integrity and security that we can do together with Dimitri and Mischa, and such that we can actually bring it together and get these opportunities there as well.
Yes, and is it already possible to say something about the requirements that you then have on quantum computing? So how can we actually measure the usefulness of these applications?
Well, to measure these usefulness, then we really need to take a look at the broader field of the architecture and to see what kind of benefits they can bring. So it's also about the implementation and the costs and the benefits that one has of these algorithms within the current existing legacies that we have, and to actually have a much more broader field, like using design thinking and systems engineering, and to really make it beneficial for the bank. So there's much more than only algorithms. There's also some part of engineering involved in it, such that, well, we hope that we can actually get some nice applications out of it.
Yeah, I can imagine. So a lot of things needed for one quantum application. Dimitri, I see you moving. Do you wish to comment on that?
Well, it's a lot of people tend to only talk about the advantages in quantum computing. I tend to say, if you look at the advantages in quantum cryptography or communication, I think that's closer at hand. You can already buy your QKD devices from Adil if you want to and use them. They're just point-to-point machines with limited functionality, but you could. And the thing is then, if you do that, you combine protecting yourself by math and nature. And then you create this uninterceptable network, so to say. It's not really uninterceptable, but you know if someone is eavesdropping on your line. So in that sense, looking at that perspective and saying that quantum cryptography, in our opinion, is if we have to choose between computing and cryptography, we'd go for cryptography and creating these high secure financial networks. And we are pretty advanced in that. And that's also due to, also one of the reasons why we started our program, by doing, you will learn so much more about how you can really apply it, And when I go back at first glance, I thought that, you could entangle qubits and send them halfway across the world. And then you could have instant communication where no one can intercept it. Well, when you start learning how it really should work, you need to send those qubits to the other side of the world, and you need a carrier for that. So and you're bound by the speed of light. So, but then that changes a lot of those possible use cases. So I would, advise people to really, really start doing this and talking to the partners, to the quantum experts, because by just listening and reading, you really don't get that, and you can take much more advantage, and there's much more opportunities if you really start doing it.
Yes, I agree with Dimitri that as a bank, you should take not quantum computing as your main concern, but a very much broader space of quantum technologies, where quantum cryptography is actually one of the application areas of. But for example, quantum random number generators could also be very useful within the banks, and so many other technologies that are arising from there as well. So to have a broad mind and to see the overlaps given with the existing architectures, to see what kind of benefits one may find here.
Yeah. We have a question also from the audience. I don't know if you can see it in your screen. But the question is, how can you also embed international partners to the Dutch quantum financial ecosystem?
Interesting question. I'm working on it right now. I don't have any answers yet, but I'm working on it, and it depends also highly where you can get funding from. If you need public and private funding, and you're also talking to the quantum flagship or the Euro QCI, you have some boundaries. So then you might not, you can't use, for instance, the dependency of the US or Asia within your value chain. So can we park that, and I'll give you an answer in maybe half a year?
So some patience is needed for international collaboration. It sounds like our Dutch financial institutes are very much open to it. I had one more question for you, Mischa, because you are the leader of the Quantum Lab at Rabobank. And I wondered what is needed to actually start a Quantum Lab in an organization?
Well, to begin with, you need to have a view about the market, what's happening outside of your bank. You need to have some perspective of what is happening inside the bank. And of course, it all starts with people. So you have to have people who are enthusiastic about the subject, people who are interested or educated on the subject of quantum and quantum technology. And then you can make a quick start of that. That's how we have done it.
So enthusiasm is at this moment one of the key elements, if I understand.
Well, also, it all starts with enthusiastic people, of course, but soon you will need more education and also awareness about what's happening and what is actually quantum and quantum technology and how you can use it and how this will reflect on your products and how this will probably change the market or pose a threat to us. So that's, but the first step is to have people, of course.
Yeah, so you need people and then a market overview and have a view on what's coming up there. And I see a question popping up in the screen, and I think it's a very interesting one. I think for all of you, but what is your current quantum budget? What are you allowed to spend in your organization?
Not all at once.
We can't give an exact figure, of course, but quantum and quantum technology is seen as one of the main technologies where we see a prospect of having a large impact within the bank. Therefore, we have allocated a small part of the total innovation budget to have a start for this. But I'm sorry, I can't give you an exact figure.
You're not talking about millions, you know. These are long-term projects, and you can't promise any product or return on investment anywhere soon. And you don't need to spend millions on these quantum projects. It's about exploring first, and you can do it with very, very limited resources. I think if you spend a couple of €100,000 a year, that would be, I think, the right spot to do. Don't overpromise. People have asked me the question, can you give us a product or a return on investment in 3 years? And I was like, if I say yes, it's going to make my life easier for the next 2.5 years. But I didn't say yes.
Yeah, don't overpromise and don't buy into the hype. Those are very important things to keep in mind. We're almost out of time for this panel, so I'm going to make a round for closing statements. Mischa, do you have any closing remarks?
I think the main thing is what Dimitri already said, is that we still need to advance in encryption. Security is one of the most important things for banks. Also already told by previous presenters, it's all about trust. As long as we can provide this trust and secure the data of our own and also of our customers, we are doing the right thing.
Thank you. And Adil?
Well, I would say that if you would like to actually get to have something, have a broad view, start playing around, learn around, just get your hands dirty on various application areas, such that you can learn from it and maybe even deliver solutions on long term. Get your hands dirty. That would be my take-home message.
Yeah, I would say the same in that regard, Adil. Start doing. And if you need my help, contact me. If you maybe want to join us in our ING, Rabobank, ABN AMRO conversations, we're happy to invite you and have a conversation on that. So don't hesitate to contact any of us and take the next step.
All right, well, thank you very much for this panel. I hope you can stick around a little longer for additional question and answers. And I see that slowly all of our speakers are coming in the screen, so welcome everybody. I'm missing speakers from Mckinsey at the moment, but I think they will surely pop up. So we're at the last section of today. So in the end, I invite everybody from the audience to ask questions. This is the chance you have, and otherwise we'll have to do it offline. I think the first question I have is, do you expect any quantum advantage in the NISC area? And maybe who better to ask than Buhrman?
Yeah, that's a great question. And it depends a little bit on what you mean by quantum advantage here, because in some sense, quantum advantage has been already demonstrated by the experiments of Google, and in some sense the boson sampling experiments from China. And I expect that when you scale these up a little bit further, then there really will not be simulable classically, and hence you have true quantum advantage. But maybe a more interesting question is, do you expect useful quantum advantage within the NISQ area? And that's a hard question to answer. And if I put on my optimistic hat, I would say yes, I truly hope so. But to be honest, we're still far away from that. We need to do a lot, and actually, I think the hardware needs to get a little bit better than it is today.
All right. So to summarize this, in order to get an advantage in the NISQ area, you need to know what you mean with this. Is this really a practical thing which you want to show, and hardware needs to continue on developing. One question I've seen from a few people from the audience, and that is, what should companies do today? What is wisdom here? Maybe Stavros, is this a question you can answer?
Yes, I think I can. They should migrate to post-quantum cryptography. At least they should prepare to do this, because it's ready. It's not at an experimental stage anymore. This is over. We will have standards in the next couple of years. It's possible. Your choice, which kind of post-quantum cryptography, which algorithm you use, will depend on your application, of course. But you have to start today to think which is your perfect fit, because it's not getting easier. So start with a good system design. Put agility and in your system design, so that you can have in the future drop-in replacements if something doesn't fit your need, maybe. So start rethinking your architecture on the basis of post-quantum cryptography.
Yeah, Joost, thank you, Stavros. Joost, you're working on architectures. Any tips for these organizations?
Yeah, I mean, I think one thing we should learn from the past here. I mean, we have migrated away from crypto a couple of times already, MD5, SHA-1, and I think there's one thing we notice is that it takes much longer than you initially anticipated. So really, if we say 10 years or 20 years, you may think, oh, that's so far away. We'll be able to do it in no time. It is most likely not true. It will take very long. So indeed, try to find where your critical systems make use of crypto and how you can migrate to post-quantum crypto now already. And like I said in my talk, it may be possible to not have to migrate your whole ecosystem immediately, but rather start with some small pieces so that you can kind of gradually upgrade instead of having to do it all at once, which may make the migration much easier.
Thank you, Joost. I see Leo, you want to react?
I just wanted to comment on what is being said. So first, for the migration, and it's a term that has been used, there are some no-regret moves. In particular, you can combine this new post-quantum cryptography with the classical cryptography. So at least for a transition period, this is a very recommendable things to do in case there's like some things to iron out in the implementation that leads to bugs. So you can do this in a way that you are sure there are no regression in terms of security. You have to use what's called hybrid or combiners that make it so that if either solution is secure, then the total system is secure. The second thing is, again, that such a migration is relatively cheap. I mean, if you're thinking of quantum investment, we're talking about about orders of magnitudes larger investment. So for a fraction of that cost, you should already be getting security from quantum threats before trying to make a business out of quantum computation.
Clear advice. Thank you, all of you who answered this question. I have another question related to data protection, and that is how should companies put the threat regarding sensitive data in the context of EU data protect laws? So I let that question sink in, and I think Stavros, I have to look at you first for this question.
I'm not sure if I understand this question right. The threat regarding sensitive data in the context of EU data protect law. Can you help me with that? I'm not sure what kind of goal is behind that question. So we are talking about relatively different things here. So the threat from quantum computing is on the. If you always talk about threats, it's rather from aiming at confidentiality, authenticity, integrity, and the EU data protect law is kind of is protecting civil rights, and so I'm not sure if I can combine those two worlds.
All right.
Could it be that it's about quantum computers will be in the cloud, so we won't have quantum computers at companies like ABN AMRO in the near future, or maybe in the or maybe ever. So what if this quantum computer is located in the US and you're sending your data to that quantum computer to perform some calculations? So what should we do then? Are we still protected? Can we trust the company, or are we forced to set up and build a quantum computing cloud in Europe?
Well, this is actually being done. So there's this EU Quantum Technology Flagship Program, and there are especially two projects financed in that. It's Acun with Q, not with C, and Open Super Q, and their goal is to build the European quantum computer. But, well, I'm not sure if you take a cloud as a service and you want to do a computation, then you will have to accept that you're sending your data away. So something you sign on. I'm not sure if you can protect your privacy when you say that I want to be a user of a cloud service. There are some kind of mechanisms like homomorphic encryption and that kind of stuff, but they are not as advanced that you can say, I am doing a calculation in a cloud service and no one knows what I'm calculating.
But should we wait for those kind of technologies to be mature enough, or maybe should we wait for fully blind computing in that sense?
You can wait, but I'm not sure if you can wait. Would take a couple of time. I think maybe take some decades until you can have fully homomorphic encryption, blind computation functionality in clouds, and I'm not sure if it will be offered to you.
Interesting discussion. We have another question from the audience. The question is quantum cryptography better than elliptic curve cryptography? Maybe Joost, can you take it?
Well, define better. I think it is better in the sense that it's secure when a quantum computer is available, whereas elliptic curve cryptography is not. I think elliptic curve cryptography is very nice, and it has very many nice properties. Like I mentioned before, like it is actually very fast and it's very small. So it definitely has many advantages over many of the post-quantum schemes. It's also easy to use within broader protocols besides just key exchange and signature. So it has many advantages. Yeah, if a quantum computer is in the future, I think we simply have no choice but to migrate away from it. And so, yeah, it's not a matter of which one is better. It's rather only one of the two is secure. So we really don't have a choice.
Well, again, there's those hybrid encryption modes where we can have the security advantages of both, but at the cost of both.
And there often the cost is dominated by the post-quantum scheme. I think you mentioned that before already as well. So indeed, it is at very little cost to do hybrid over simply post-quantum. So it is indeed a very good option.
All right, thank you. I see another question, and also one popping in the screen. It's about the payment systems. What if we replaced triple DES in the payment system? What should be the AES key size we should aim for? So I'm looking at the banks to answer this one.
256.
So AES 256 to start with.
Yeah, they'll be safe for the coming 20 years.
All right, well then...
if you put it on one line, then you could enter with AES 128. But if it doesn't, from the pre-quantum security level, but if it doesn't hurt you, then go with AES 256. I would agree absolutely with this. So it depends on your security level you want to have. So as I mentioned, AES 128 is NIST security level 1. If this is enough for you, then at least you have entered the world of this post-quantum. But again, if it doesn't hurt you, take AES 256.
Yeah, we need
this
to upgrade.
This is also a recommendation of the BSI.
We need to upgrade, so why not immediately go to 256 instead of 128?
Yeah. So AES 256, I guess, is the answer, without knowing anything about your constraints. Okay.
Yeah, so I see consensus has been reached within the panel on the key length, so go for 256. There is one more question. Who are the big players in quantum computing? Which ones are well funded? Harry, do you know the answer to this one?
I mean, there's sort of several sides to this question. You have big companies that are big players in quantum computing, like Google and IBM and Microsoft, and forgetting a few. So those are big players, and they're well funded. But then you also have the academic side, and there you have big players in terms of universities and centers, like, for example, in the Netherlands, Qsoft and QTech, but you also have them in Canada, for example, IQC, and also in Europe you have a bunch of other ones where you have a sort of a coming together of very good academics who have been working in the field for a long time, and they are getting also good funding. So yeah, I would say that those are the big players, and they are getting funding, though since the field is growing, more funding is needed, and hopefully is also underway.
Yeah, and then another question, is funding the most important thing here? I often hear about the war on talent versus funding.
Absolutely. So yeah, the funding is just one part. You can set a pot of money, and then you can pay people to do something, but of course you will need these people. And currently, I think the resources are scarce. It's the fact that many countries and many institutes and many big companies have money, and they are attracting, and they want to attract the best talent around. But of course, there is an end to that, and the way to get new talent is to do education, and to raise a new army, so to speak, of people who know about quantum computing and quantum technology in general. And that's what the universities are doing throughout. For example, here in the Netherlands, we have a program. We're trying to set up a national program, and also locally there are big programs for quantum computing and quantum technologies. And you see the same thing happening in other countries around the world. So education is super important here as well.
All right, thank you, Harry. I think we have time for one more question. And oh, there's a test from Roelof. I'm not sure how to read this, but the question is to Leo. Would you have a specific homomorphic solution in mind? Re-adding my earlier question. I don't think we have seen your earlier question, Roelof. But Leo, any comments on specific homomorphic solutions?
So I mentioned this during my talk, but did not explain what it is. So maybe some of you already know. But homomorphic encryption is a technique invented 10 years ago that allows to compute on encrypted data. So that's something useful for maintaining privacy in the cloud. And we're over 10 years, we've made great progress in terms of reasonable efficiency, but that's something that is terribly inefficient compared to normal computation. We're talking 1 billion times more costly. So there are many homomorphic solutions available. Some are better depending on the problem that you want. Most of them are resistant to quantum attacks because they're based on lattices. But yeah, I cannot recommend one over another. It's really use case dependent.
All right, so Roelof, depending on your use case, I think Lea would be open to answer your question offline. And looking at the time, I see that we have to go offline in exactly 1 minute. So I hereby would like to thank our panelists, not only of course for their participation in the panel, but also for their presentations. So thank you very much. And I also would like to thank our host. Oh, I see we have a score already in. Oh, thank you. Keep climbing. Just press 1-0, and we would be very pleased with that. 1-0, very concretely, not either 1 or 0 that we would like. But I would like to thank our host for today, the Dutch Payments Association, and also Quantum Amsterdam. So thank you for organizing this event, and to all our viewers, thank you so much for your time. And I hope you have learned something today. And that is presentations of all the fantastic speakers we had today helps you on your quantum journey.
Thank you.